Hey guys, welcome to our lecture for Math 112, section 6.2, right triangle trigonometry. So last lecture, we talked about angles and their measures and how we talked about those and things like that. Another big aspect of trig, or Math 112, is triangles, and specifically right triangles. Those are really what define what we deal with. So very simply, if for those of you guys who don't know, a right triangle is any triangle that has a 90-degree angle for one of its three angles. And remember, all three angles have to add up to 180, so make sure you guys are keeping that in mind. And so the standard labeling, so if we say, given a triangle in standard labeling, this is what we mean. And so for this triangle here, we've got our right angle there. Then this vertices is A, B, C. Those are all capitals. And then the side opposite those angles is the lowercase version. So, the side opposite those vertices. So this side here we would say is little a, this is little b, and little c. And then the angles themselves, we use Greek letters to represent those. And so for a right angle, we always make it a square. Otherwise, it's just something like, sorry about that. Otherwise, something like this. And so we use the Greek letter alpha there. We use the Greek letter beta here. And this is the Greek letter gamma. So if you know the Greek alphabet, it goes alpha, beta, gamma, A, B, C. So it kind of all ties in. And so this is our standard labeling for a triangle, where our vertices are capital normal letters for us, our Roman letters. The side lengths are the lowercase Roman letters, and the angles themselves are the first three Greek letters. So that's the standard labeling for a triangle. Now we also need to talk about something called similar triangles. So we say that two triangles are similar, and we use this notation. So if you think back to algebra, when we said something like 1/3 is approximately 0.33, right? We would do kind of a squiggly equal sign. So similar is just a single squiggle. So two triangles are similar if they have congruent corresponding angles. What does that mean? That just means that the angles are the same, but the side lengths may be different. Okay, and kind of our annotation that we would use here. So for this triangle here, we have two triangles. We've got let's do red for one and blue for another. Okay, so we've got two triangles right here, right? Now I'm gonna get rid of that because it just makes it a little sloppy. And so what I'm going to do is I'm going to label the smaller triangle in standard labeling. So just with the vertices, so we have our A, B, and C. And then especially in a situation like this, what we'll actually end up doing is we'll use a little kind of apostrophe. And so I'll say that this is B prime and C prime. And that's our way of kind of annotating our second larger triangle. So it would be that triangle would be A, B prime, C prime, whereas our first triangle is A, B, C. Now, we also can annotate the angles themselves kind of and differentiate them. Obviously, this angle here is the same in both triangles because it's the same vertices, same lines. But then we can also say that these two angles are the same, and these two angles are the same. Now, I used color, but obviously that's not always the case. But what you can also see is that I did a single line for the angle beta and beta prime, double line for angle gamma and gamma prime, and a triple angle line for angle alpha. Now, I didn't label those as alpha, beta, and gamma, and I'm just kind of saying those referring back to our standard labeling. Okay. And so what's really cool with this is we can get proportionality with these side lengths, and we can get these proportional ratios that can really help us out. Now, I just want to give a real quick symbol notation. And we can say that because of this, so we have triangle ABC is similar to triangle AB prime, C prime. And so this may be some notation that you see. And if you see this, just know that all of the corresponding kind of angles are the same, are equivalent, and side lengths may be different. So one thing that's really kind of cool is the corresponding sides of similar triangles are proportional. So what that means is we can set up these proportional ratios, and we can say things like side BC, the length of BC over, say, the side AB, that's equivalent to the side B prime C prime over A B prime. So what in the world am I looking at? Well, okay, so first we have side BC, so that's this side here. We're dividing that by side AB. Okay, so the length of this side here divided by the length of this side here, that is equivalent to the length of this side here divided by the length of this side here. So that ratio is the same, and that's true for any ratio of sides you create. And you can even mix the triangles together, and I'll show you that in just a sec. So we could even do something like BC over B prime C prime is the same as AC over AC prime. Okay, and so it's really kind of cool. These things are really nice and useful for us to be able to do. Now, on these right triangles, we are going to utilize the trig functions. There are 6 trig functions, if you remember. And I will write out both the full name of them, and then it's kind of abbreviation, and that's abbreviation is kind of the way we use it in function notation. And so we have the sine function, the cosine function, we have the tangent function, and that is sine, cos, tan. And then we have 3 more, that is the cosecant, secant, and cotangent. Okay, and cosecant is CSC, secant is SEC, and cotangent is COT. Now, I arranged these in this way because there is some kind of tie-ins, and let's have a little fun with this. Let's see, okay. Where's my pen? There we go. These sets of trig functions pair together, and it allows us to kind of really work with them. And you'll see as we start to define what they are, how they work, and everything like that, and use them in that way. Now, there's 3 more terms that we need to talk about before we can really get into how to evaluate these trigonometric functions. So if we're given a right triangle, such as this one right here, and we are given some, I like the Galaxy pen, but we're going to stick with black for this. So we're given some angle theta. That is an acute angle in a right triangle. So basically, it's just either of the 2 angles other than the right triangle, or the right angle. Based on this angle, we have the 3 sides have a name. So this side here that is opposite of our angle is called the opposite side, and we'll abbreviate that OPB. The side that is next to it that is not opposite of the 90 is called the adjacent side, and we'll abbreviate that ADJ. And now you may remember this from geometry classes in the past. The side opposite the 90-degree angle is called the hypotenuse. Called the hypotenuse. And we'll abbreviate that HYP. I know this kind of looks like a mess, and kind of is. But we can use that. So then for this angle theta here, this angle that we're talking about, we can evaluate all of these 6 trig functions using ratios of sides. That's how they are defined. And so we say things like the sine of theta is equal to the opposite over hypotenuse. cosine of theta is adjacent over hypotenuse, and tangent of theta is equal to the opposite over adjacent. Now, for those of you that have taken some other classes that may have done some trig, there's a nice little acronym, and we're going to talk about that in just a second to kind of help us remember this. Now, remember how I said up here that the sine, cosecant, cosine, secant, tangent, cotangent are linked. This is how they are linked. So I'm running out of room right next to it, so I'm going to go to the other side of this triangle. So the cosecant of theta is equal to the hypotenuse over the opposite. The secant of theta is equal to the hypotenuse over, hypotenuse over the adjacent, and the cotangent is the adjacent over the opposite. So notice if we look at these, grab a different color. Okay, the sine of theta is opposite of our hypotenuse. Cosecant, which was linked to sine, is hypotenuse over the opposite. So they're very simply just the inverses of each other. So they're the fractional inverses. So in other words, just flip that fraction over and we get it. Okay. Now, the acronym that many of us have used to remember all of our sine, cosine, and tangent evaluations, this set of a piece of information right here is TOA. And that is that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And so that is a nice, fun little acronym that we can use to remember these ratios for sine, cosine, and tangent. And then if we can just remember which they pair with, cosecant, secant, and cotangent, and we remember which one they pair with, whether it's sine, cosine, or tangent, it's just the opposite. It's just the flip. And so the way I remember which one pairs with which is that no co goes together. So that means cosine does not pair with cosecant or cotangent. So cosine pairs with secant because that is the only one of these three that does not have a co. Sine goes with cosecant, it's just the same way that sine and cosine, secant and cosecant, and then tangent, cotangent, they both have tangent in them, so that's pretty easy one, hopefully. So that is our kind of basic definitions of these trig functions and how we can evaluate them on a right triangle. So these are for acute angles on a right triangle. Okay, I want to make that very specific here. This fact that sine is opposite of her hypotenuse is only applicable if theta is an acute angle in a right triangle. Okay, we will look at how to deal with sine of say 180 or even sine of say 494. We can even talk about sine of say negative 3 pi over 8. Okay, so we can do all sorts of things like that, and we will deal with those later. But right now we're just sticking with right triangles. Now this is an oldie but a goodie. Good old Pythagorean theorem, just to remind us all to find the side lengths of a right triangle. We have this lovely theorem that a squared plus b squared equals c squared. So what this simply says is if we square the two shorter legs of a right triangle and add those together, that will be equivalent to the square of the larger side. If you're interested in a proof of this theorem, Google it. There's a ton of different ones out there. And it's kind of a nice, fun little proof that's usually very visual and stuff like that. It's not a crazy mathy thing. So feel free to go into that. I'm not going to do that here. That's not what this class is about. So we have this triangle, and we need to find the 6 trig functions given this triangle. But what are we missing? Right? We are missing a side length. So the first thing we have to do here is use the Pythagorean theorem. And so we just set this up. We know that A is equal to 8 and C is equal to 17. Those are terrible lines, but we're good. So we can replace those in the Pythagorean theorem, and we get that 8 squared plus b squared equals 17 squared. So we just go through and apply mathematics using our calculator, right? So we can subtract 8 squared from both sides. You could square these first, but I'm just going to do this so that way my calculator can do it all for me all at once. And then we square root both sides. That cancels out. B equals. And so if we use our calculator, 17 squared is 289. 8 squared is 64. So if we do 289 minus 64, we get a lovely 225. And then the square root of that is 15. So B equals 15. Now, quick question. Why do I not have to do plus or minus 15? Well, it's very simple. This B is the length, right? It's the length of this side of the triangle. Can that length be negative 15, whatever these units are? No, right? So it has to be the positive. So we don't have to worry about the plus or minus when we square root both sides here. So we get that B equals 15. Now, what about our trig functions? Well, because I am here's our theta. So that might be a little less confusing now. So we have to specify which angle we're dealing with. And so this is going to be our theta here. And so we have our sine theta, cosine theta, tangent theta, cosecant theta, secant theta, and cotangent theta. Okay, remember, SOHCAHTOA. So sine is opposite over hypotenuse. So here, because this is our angle, the opposite side would be B, which is 15. C is 17. So we have 15 over 17. Cosine is the adjacent over hypotenuse. So that would be 8 over 17. Tangent is opposite over hypotenuse. Or sorry, opposite over adjacent. So it's 15 over 8. No triangles, please. Okay, now how do I do these other ones? Well, remember, these are all tied to another. So cosecant, sine, secant, cosine, cotangent, tangent. So these are all tied together, and they're just the flip. So if cosecant theta is the flip of sine theta, and sine theta is 15 over 17, that means that cosecant is just 17 over 15. Secant is tied to cosine. Cosine is 8 over 17, so secant must just be 17 over 8. Cotangent is tied to tangent. Tangent is 15 over 8, so that means cotangent is 8 over 15. And there we have it. There are our 6 trig functions for this given angle theta. Okay, good job. All right. Now let's do an example with an application here of trig functions in a right triangle. Angle of elevation and angle of depression. So these are two things that are very important to figure out. So first of all, angle of elevation is, imagine if you are standing on a surface and you are looking up. Okay, that is the angle of elevation. Okay. And then angle of depression, think of it like this. If you are standing on the edge of a cliff and you look down, that is the angle of depression. So depending on whether the problem is looking up type problem, an angle of elevation type problem, or an angle of depression looking down, that is kind of the best way to think about it. Think of it as it's looking down. So in this example here, we have a company safety committee recommended that the floodlight be mounted in a parking lot as shown in the figure. So as to illuminate the employee exit. Find H to the nearest tenth of a foot. So they're wanting the floodlight to be mounted 52 feet away horizontally from the door, such that the light shines its light on the door at an angle of elevation of 37 degrees. And we need to figure out what that height needs to be. Well, how do we do this? Well, what we have to do whenever we're dealing with problems like this, we have to identify which of the trig functions do we know, do we have. Now, we're always going to use, let me say, we're pretty much always going to use sine, cosine, or tangent for many reasons. One of them being that those are the three buttons that are on our calculator. We have sine, cosine, and tangent on our calculator. And so we can use those very quickly and easily. So when we're looking at that, we have to say, okay, so our angle is this angle here. What sides do I have information for? I don't know the hypotenuse length. So sine and cosine aren't really going to be very helpful because I don't know the hypotenuse. And so that's one piece I'm already missing. And then to try and find h, that would give me two pieces I don't know, and it wouldn't help me out. But tangent involves the opposite side, which is the h we're looking for, and the adjacent side, which we know is 52 feet. So we want to use tangent in this problem. So we can set this up. We can say, okay, well, that means that the tangent of 37 degrees is equal to, now tangent is opposite over adjacent. Our opposite side here is h. Our adjacent side is 52 feet. All right, this looks like something we could solve. So before we deal with anything, let's just get h by itself. And the way we do that is very simply multiply by 52. That cancels, multiply by 52. So what we end up with is 52 tan 37 degrees equals h. Now, right now, I want you to grab your calculators. If you don't have them on you, shame on you. This is a math lecture. You should have your calculators. But take a second, pause the video, get your calculator. Remember, your graphing calculator. I'm using a TI 84 Plus. Okay, so I'm going to give you a second to get your calculators now. All right, welcome back. So we have our calculators. There's a very important thing we need to do. If you have any TI 83 or 84, these steps are going to be the same. If you have a Casio or anything else, you're going to want to Google these steps. I don't have one of those in front of me, and I don't remember the steps off the top of my head. So you're going to want to Google the steps to change your mode from degrees to radians, radians to degrees. Okay, so this problem here is giving us an angle in degrees. So we need to make sure our calculator is in degree mode. The way we do that is by simply hitting the mode button, which if you look at your calculator in 83 or 84, should be up towards the top, usually second row in from the left. So right next to the second button, it says mode. Click that. Now, if you look down, I believe it's about the third option down in most models. It is on mine. You'll see there's radian and degree. Make sure that the degree is highlighted. If it's not, go down to that row, use left or right arrows to get you so that you're highlighting over degree and hit enter. Now that degree should be highlighted in bold. If you move down, it should remain highlighted. That means your calculator is now in degree mode. Now remember, degrees and radians are different, right? 1 degree is not 1 radian. And so we have to be careful that we have our calculators in the right mode. So if I said tan of 37 and my calculator was in radians, it's going to take the tangent of 37 radians, not 37 degrees. So we want to use our calculator to do this. So we can do it all at once, or you can kind of do it piece by piece. I'm going to do it piece by piece just so that you guys can make sure you're in the right mode. So if you do type tan 37, you should get 0.753554 and then a couple more numbers, okay? If you're not getting that, you're not in the right mode, and go back into mode, make sure that you are in degrees. If you are for sure in degree mode, and you're still not getting this, send me a message. We can hop online and we can figure this out. Okay, so 52 times tan of 37. And what do we get? We get 39.1848106.1, but we needed to find h to the nearest tenth of a foot. So that would be that 39.2 feet, approximately h. And there's our answer. Okay, pretty cool, right? So these problems aren't too crazy. The hardest thing sometimes to do is to remember the SOHCAHTOA, right? To remember sine involves opposite and hypotenuse, cosine is adjacent hypotenuse, tangent is opposite and adjacent. And being able to identify which of those functions is going to best suit your needs for this problem. Okay.